Hi everyone, now we are at lecture number 6, sequences and series. So this problem I have given exercise in the last class, second method, first method I did and second method I have given exercise. Let me do it, just verify your answer. So till this I have done uh, limit intensity and adjust like this because if you apply directly limit you will get 0 by 0 form, therefore you have to apply L'Hopital rule. Okay. L'Hopital rule. This rule you have to apply here. Okay. That means numerator differentiation separately and denominator differentiation separately. Then let us proceed. Limit n tends to infinity. Yeah, numerator differentiation. Derivative of u by v. What is this derivative of u by v? V square and numerator derivative u dash into denominator as it is minus numerator as it is into denominator derivative. So this is u by v differentiation. So same formula I want to apply here. So limit n tends to infinity. Yeah. So apply numerator derivative. So it will be n minus 1 by n plus 1. So ln derivative, right? So 1 by ln x is 1 by x. So 1 by x means it will become reciprocal of this into, and its derivative, so n minus 1 whole square, right? And numerator derivative n plus 1 derivative is 1 and denominator n minus 1 as it is, okay? Minus numerator n plus 1 as it is and denominator n minus 1 derivative is 1, okay? Whole divided by denominator derivative minus 1 by n square, minus 1 by n square, okay? This is after differentiation, okay? Yeah, let us simplify this. So limit n becomes large, limit n tends to infinity. Yeah, so n minus 1 upon n plus 1, okay? And here what will remain is n cancel out, so minus 2, so minus 2 upon n minus 1 whole square, n minus 1 whole square, okay? Whole square this one, and denominator minus 1 upon n square, minus 1 upon n square. What left? So anything get common or that cancels? Yeah, so look at here n minus 1, one time n minus 1 will cancel out, so 1 n minus 1 will remain, and minus minus get into cancel, minus minus get into cancel, so 1 by n square become n square by 1, so 2n square by n plus 1 into n minus 1, that means n square minus 1, okay? So therefore it will be, so limit n tends to infinity, limit n tends to infinity, 2n square divided by n plus 1 into n minus 1 is n square minus 1. So this is, in the next step you take out n square common from both numerator and denominator, that will be cancelled out. So n square into 2 divided by denominator n square is out, so 1 minus 1 upon n square, okay? Now this n square is out, cancel, so what left? So 2 upon 1 minus 1 by infinity, so you get just 2. So therefore limit n tends to infinity. What is this actually? Look at, go back. So it is limit n tends to infinity, ln of a n value, right? 2. So limit n tends to infinity, limit n tends to infinity, ln a n value is 2. This one is 2. So therefore limit n tends to infinity. So here nothing is there means base e, right? This is base e. So send this to this side, reciprocal of that. So therefore limit n tends to infinity, only a n value how much? E power 2. That's it. E is going this side, e power 2. So therefore finally the given sequence a n, okay, which is converges to e square as n tends to infinity. Check your answer. Hope you have done already. Check your answer. Answer is e square. The given sequence is converges to e square. Next, continuation, problem number 12. Yeah, somewhat logical. So look at carefully. Solution. First one. Look at here. The sequence. First term is 0. Second term is 2. Third term is 0. Fourth term is 2. fifth term 0, sixth term 2, like that, 0 2 0 2 0 2. So if you go to large number position, let's say infinite number position, so what is the number will be at infinite position? That is, so it will be two options. It can be either 0 or 2 because both the numbers are reaching, right? 0 and 2 0 2 0 2 0 2, like that. So therefore, let's say this is L1 and this is L2. So you're having two different limits. So therefore, the given sequence An is diverges. So here L1 is 0 and L2 is 1. So therefore, they are not equals to. Okay. So 2, right? This is 2. L2. So therefore the given sequence An is diverges or not converges. Is diverges. Diverges. Similarly, look at the second one. Minus 1 plus 1 minus 1 plus 1 minus 1 plus 1, again same story. So if you go to at infinite position, what will be the number at infinite position? What will be the number? Again here two options, either it can be minus 1 or plus 1. So again same story. So here L1 is minus 1 and L2 is plus 1. Same problem I did by using subsequence concept. Okay, look at, by subsequence concept I did. So again same story, therefore the sequence An is not converges or diverges, whatever, diverges. Okay, and third one, look at third one, 1 1 1 1 1 up to so on. So therefore if you go to at infinite position, what will be the guessing number? The guessing number will be 1 only because it is 1 only repeating, right? So therefore it reaches to 1. So it is a constant sequence. So every constant sequence converges to the same number, right? So therefore limit n tends to infinity, An is nothing but limit n tends to infinity, An is nothing but 1. So is nothing but 1 only. So limit value is L, which is finite. Some finite number existed, therefore the sequence is converges. Therefore the given sequence An converges to 1. An converges to 1 as n tends to infinity. It is converges now. Okay. Now look at fourth problem. Fourth problem, minus 1 plus 2, minus 3 plus 4, minus 5 plus 6, minus 7 plus 8. So if you go to it infinite position, what will be the number at infinite position? What will we get here? So again here two options. We will get either plus infinity or minus infinity. Because you look at in negative side, minus 1, minus 3, minus 5, minus 7, minus 9 up to so on. So it will go to minus infinity. Positive side 2, 4, 6, 8. So it will go to plus infinity. So again it is having two limits. So plus or minus infinity. Therefore again the sequence An is diverges. Okay. Similarly fifth one. Look at fifth one. Is an interesting one. Minus 1 plus 1, minus 1 plus 1, minus 1. Look at first five terms. First five terms are, we are unable to find the limits, but after fifth term you are getting 3 3 3 3 3 only. So here you write comma dot because it is sequence, right? Sequence means infinitely many terms. Yeah. So after that, how many terms are repeating? How many terms? There are infinitely many terms are threes. Therefore, this sequence is going to which number? 3 only. If you go to a large number which is infinite, let's say infinity placed number is 3. Therefore, the sequence is converges to 3. Therefore, the sequence A and here converges to 3. Okay. See, you may get doubt here. What about first five terms? Don't worry about first five terms because you look at the definition. What is the definition? According to definition, modulus of an minus L, okay, an minus L is less than epsilon for some epsilon positive, right? This is true for all n more than capital N, right? More than capital N. More than capital N I have written. That means what? After certain stage, for example, n is equal to here for particular problem, it is 6. So n is equal to 6 means for sixth term onwards, each and every term lies in this interval. How many terms? Infinitely many terms are lying in this interval. So don't worry about first few terms. Here first few terms are 5. So don't worry about this first few terms. No need to worry. What I want, after certain stage, infinitely many terms need to be satisfied this condition. Not all the terms. Only after certain stage terms we need to satisfy. After certain stage means here certain stage is 6. So after sixth term onwards, or fifth term onwards. That means sixth, seventh, eighth, ninth, 10, all these terms are need to be satisfied this condition. Same thing happened here. Okay, so L minus epsilon less than an less than L plus epsilon. This I'm expanding it. So that means what, an is lying in the interval L minus epsilon to L plus epsilon, L plus epsilon, right? And this is true for all n is more than some capital N, right? Now let us choose. So here L is 3, right? For this problem, so 3. Let us choose epsilon. So L is 3. Let us choose epsilon is whatever. Let us choose 1. If epsilon is 1, what will we get? It is 2. So 2 comma L is 3, epsilon is 1. So 4. So here particularly an is belongs to this interval for all n more than capital N, which is number 6 I'm writing. That means sixth term onwards, more than or equal to 6 I'm writing. So from sixth term onwards, that means what is sixth term here? 3. Seventh term 3, eighth term 3, like that. So how many terms are lying in this interval? So here there are infinitely many terms are lying in this interval. 2 to 4, right? 2 to 4, 3 lying. How many terms? Infinitely many terms are lying from sixth term onwards. Therefore, the sequence converges to 3. See, you choose epsilon is equal to, for example, let us choose 2. If you choose 2, what will be the interval now? Epsilon is 2. So 3 minus 2, 1. Okay. Now 3 plus 2, 5. 1 comma 5. In this interval 3 lying. Look at again how many terms? Again infinitely many terms. Not only for few epsilons. You can take any of the epsilon. This definition is true for all epsilon positive. Look at the definition. For all epsilon positive, it is true. So therefore the condition is holding. So therefore we no need to worry about first few terms. First few terms means before sixth term onward. Before sixth means first 1 to 5 terms. First 5 terms we no need to worry about for this particular problem. Okay. So infinitely many terms need to satisfy the given condition. Therefore the given sequence is converges to 3. Next continuation problem number 13. Yeah, this is somewhat interesting. Prove that the sequence where Sn is this is convergent. So let us take nth term of the sequence is 1 upon 1 into 2 plus 1 upon 2 into 3. It is not 2.3, 2 into 3, okay? 1 upon 3 into 4 plus up to so on plus 1 upon n into n plus 1, n into n plus 1. Now same, what you have to do, you have to apply n tends to limit n tends to infinity to the nth term. Limit n tends to infinity Sn. So limit n tends to infinity. What is Sn now? 1 upon 1 into 2 plus 1 upon 3 into 4, 2 into 3, right? 2 into 3 plus 1 upon 3 into 4 plus up to so on plus 1 upon n into n plus 1, n into n plus 1. Okay. Now look at, I want to apply some logic here. Limit n tends to infinity. Look at inside bracket. 1 by 1 into I can write 1 minus half I can write. Check once. 1 minus half. If you take LCM, we need 1 by 2 only. Plus similarly, the second term I will write as 1 by 2 minus 1 by 3. Can I verify once? Let us take LCM 1 by 2. 2 into 3 is 6. And 2 1s are 2. So 2 3s are. So 3 1s are 3 minus 3 2s are. So 2. You are getting 1 by 6. Look at. I am getting 1 by 6 only. 1 by 2 into 3. 1 by 6. Similarly, 1 by 3 into 4 I can write as 1 by 3 minus 1 by 4. 1 by 3 minus 1 by 4. Look at here. This 3 and 4 only I am writing 1 by 3 minus 1 by 4. Look at 3 and 4. 1 by 3 minus 1 by 4. Take LCM again, we will get the same. So similarly, up to so on, the last term will be 1 by n minus 1 by n plus 1. Again take LCM and simplify, you will get the same. Why I am writing like this, will understand. So limit n tends to infinity. Now look at, most of the terms will be cancelled out. Look at here. Minus 1 by 2 plus 1 by 2 cancel out. Minus 1 by 3 plus 1 by 3. Similarly, minus 1 by 4, in this bracket will get plus 1 by 4. Likewise, up to so on. Can you guess what will be the before term? So 1 by n into n plus 1, right? What is the before term? 1 by n minus 1 into n, right? This is the before term of this one 1 by n into n plus 1. So before term is 1 by n minus 1 into n. So this I can write 1 by n minus 1 minus 1 by n. Check once. Take LCM again, will get the same. So likewise, so this minus 1 by n will be cancelled out with this plus 1 by n. So likewise, each and every term will be cancelled out. So first term and last term will be left. So therefore this will be, so first term is 1 minus last term is 1 by n plus 1. Now you apply the limit, you will get 1 minus 1 by infinity. So therefore you will get 1. Therefore the given sequence Sn is converges to 1 as n tends to infinity. So therefore the given sequence is converges to 1. Similarly, problem number 14. If nth term of the sequence is this, then verify the convergence status of the sequence Sn. So this is somewhat again interesting problem. So the nth term Sn is 1 upon n plus 1 plus 1 upon n plus 2 plus 1 upon n plus 3, okay, plus up to so on plus 1 upon n plus n. This is nth term. So this problem is not like previous problem. If the sequence is increasing sequence, according to theorem number 5, if it is bounded above, then directly it is converges. Your question is at what number the sequence converges. That is not the question. Question is it converges or not? That's it. So therefore by theorem number 5, if the sequence is increasing, if it is bounded above, then directly I can say that the sequence Sn is converges. Okay. So once let us verify, is it increasing sequence or not? So Sn plus 1, n plus 1 term of the sequence. So wherever n, there you write n plus 1. So n plus 1 plus 1. Okay. Plus 1 by n plus 1 plus 2 plus 1 by n plus 1 plus 3 plus up to so on plus 1 by n plus 1 plus n plus 1. So if you simplify this, you will get 1 by n plus 2, 1 by n plus 3, okay, plus 1 by n plus 4 plus up to so on plus 1 by 2n plus 2. So this is Sn plus 1. Now let us verify whether the given sequence is increasing or decreasing. So Sn plus 1 minus Sn. What is this? First Sn plus 1. What is Sn plus 1? This one 1 by n plus 2, 1 by n plus 2 plus 1 by n plus 3, okay, plus up to so on. What is the before term? 2n plus 2. Before term is 1 by 2n plus 1 and 1 by 2n. So 1 by 2n plus 1 by 2n plus 1. Just few before terms I am writing, okay, plus 1 by 2n plus 2. 2n plus 2. So this is the last term, right? Before these two term will be there. What is the before of this? 2n minus 1, 1 by 2n minus 1, like that. So this is Sn plus 1, okay, minus, what is Sn? Sn is 1 by n plus 1 plus 1 by n plus 2n, right? Now you observe the terms, look at minus 1 by n plus 1, so plus 1 by, so it is not getting cancelled, sorry. So n plus 1 is not getting cancelled. Which one will getting cancelled? So minus 1 by n plus 2 cancel, here plus 1 by n plus 2. Plus 1 by n plus 3, next 1 by n plus 3, minus 1 by n plus 3. And 1 by 2n, minus 1 by 2n, out. Understood? So what are left now? Only these two terms and first term of here. So therefore finally I will get, so 1 by 2n plus 1, 1 by 2n plus 1 and plus 1 by 2n plus 2. These are from the first bracket, and from the second bracket minus 1 by n plus 1. So these three terms are left after cancelling out the similar terms. Then take LCM. What will the LCM? 2n plus 1 into 2n plus 2 will be the LCM, because this is 2 into n plus 1, right? Already this is n plus 1, that's why. So then simplify this. Yeah. So 2n plus 1 is gone, so 2n plus 2 here, 2n plus 2 2n plus 2 plus 2n plus 1 is gone, so 2n plus 1, and here minus 1 n plus 1 is gone, so 2 into 2n plus 1, so 2 into 2n plus 1. Okay, and if you simplify this, what do you get? So 2n plus 2 and 4n plus 3, here 4n plus 3, and minus 4n plus 2, minus 4n minus 2 upon 2n plus 1 into 2n plus 2. Okay, and look at here, 4n minus 4n is out. What will be? So this will be 3 minus 2, so 1. So 1 upon 2n plus 1 into 2n plus 2. What is n here? Since n belongs to natural number set, so this denominator is not negative, never negative. Numerator is already positive, therefore this is more than or equal to 0, since n belongs to natural number set. Clear? So this is more than or equal to 0. Therefore Sn plus 1 minus Sn is more than or equal to 0. So therefore Sn plus 1, okay, minus Sn is more than or equal to 0. So therefore clearly Sn plus 1 is more than or equal to Sn, which is true for all n. So therefore the given sequence Sn is increasing. So it is increasing sequence. Next, if we show if it is bounded above, then we are done. Okay, it is increasing and bounded above, therefore the given sequence is converges. Now let us verify whether it is bounded above or not. So what is Sn now? Sn is nth term of the sequence starting with n plus 1. So 1 by n plus 1. So 1 by n plus 1. Next term is 1 by n plus 2 plus 1 by n plus 3. Okay, plus up to so on. The last term is 1 by n plus n. So this is the nth term of the sequence. Now we need to show that if it is bounded above, then we are done. So for that, what I am doing is, let us find the upper bound for that. So before that, look at n plus 1 is always more than n, right? For all n belongs to natural number set. Okay, for all n belongs to natural number set, n plus 1 is always more than n. So clearly n plus 2 is also more than n only, right? And n plus 3 is also more than n. So up to so on, n plus n is also more than n. Okay, so can I write this one is 1 by n plus 1 is less than 1 by n. I am reciprocaling, therefore inequality changes. Okay, and this one 1 by n plus 2 is less than 1 by n. I am reciprocaling, nothing else. And clearly, what is this? 1 by n plus 3 is less than 1 by n. Okay, and what about this? 1 by n plus n is less than 1 by n. So all these things I want to use here. So now this will be, look at, observe carefully, less than, strictly less than. Look at the first term, 1 by n plus 1 is less than 1 by n, right? Look at this one. By first inequality, I am writing this is less than 1 by n. Similarly, second term 1 by n plus 2. Look at 1 by n plus 2 is also less than 1 by n. Therefore, plus second term also less than 1 by n. Okay, and similarly, third term also less than 1 by n. So 1 by n. So plus up to so on. The nth term is also less than 1 by n. So 1 by n. So total how many terms? N terms. N terms total. Because look at n plus 1. 1 means it is first term. N plus 2. 2 means second term. 3 means third term. N means nth term. Total n terms. So therefore this will be n into 1 by n. Total n terms 1 by n. So this will be 1. So therefore finally what I can say is, so therefore Sn is less than 1. It is less than 1. So therefore the sequence Sn is bounded above. Is bounded above. So therefore sequence Sn is increasing. It is increasing and bounded above. So therefore the sequence Sn, the given sequence Sn is converges. That's it. I want whether it is converges or not. That's it. At what point it is converges, not required according to problem. So therefore, it is increasing sequence which is bounded above. Therefore, compulsory it should be converges. And particularly, it is converges to its supremum, right? It's converges to its supremum. Yeah. Continuation. Yeah, one theorem. Theorem number 7 is an interesting theorem. Sandwich theorem for sequences. Sandwich theorem. Look at. So in this three sequence, we have to take three sequences A n, B n, and C n. Be a sequence of real numbers such that nth term of Bn is less than or equal to nth term of middle sequence is less than or equal to nth term of first sequence less than or equal to nth term of third sequence. It is true for all n beyond some index n. N beyond some index n means n is more than capital N. Its meaning. So n is more than capital N can be written as n beyond some index n. Beyond means what? After. Beyond some index n. Beyond capital N. Beyond capital means what? After capital N. After capital N means what? N plus 1, n plus 2, capital N plus 1, capital N plus 2. That means n is more than capital N. That means n beyond some index n. So, first few terms may not satisfy this inequality. Okay, this is the entry pass for sandwich theorem. If three sequences satisfying this condition, then only we can apply this theorem. Okay, for example, first few terms, let's say first 5 terms are not satisfying this condition. Which condition? An should be lies in between Bn and Cn. That means An is more than Bn and An is less than Cn, like this. Then don't worry about that. After certain stage, after let's for example n is equal to 10. After 10th term onwards, if all the terms are satisfying this condition, then that is more than enough. That's it. We can apply the theorem. Okay, we need to satisfy all the terms of the sequence need to satisfy this condition. Okay. Yeah, then what is the condition? Look at, if limit n tends to infinity Bn and limit n tends to infinity Cn are converging to L, that means what? Upper and lower bounds. Bn means lower bound, Cn means upper bound. If both upper and lower bounds are converging to L, then this middle one Cn also converging to L. That means, let me write here. So Bn less than or equal to An less than or equal to Cn. Okay, if this lower limit and upper limit both are converging to L, then this middle one also converges to L. Therefore, you write here. Therefore, this is if Cn converging to L and if Bn is converging to L, then the middle one also converging to L. Here, what is the entry pass? This condition need to be satisfied, and here you need to choose proper lower bound and upper bound such that both are converging to same limit L. Such kind of upper and lower bounds only we need to choose. Okay, let me do some problems, then it will be very clear. Problem number 1. Find the convergence status of this sequence. Already this problem I did by the concept of subsequences. Same problem we can attack by using sandwich theorem also. How to attack? Look at. Let us take the nth term of the sequence is minus 1 whole to the power of n by n. So this is the nth term of the sequence. Now what I'm doing is modulus on both sides. So minus 1 whole to the power of n divided by n. So this I can write as this one is less than or equal to 1 by n. I can write. Can I write? Because it is minus n plus. So always 1 will be the supremum. So therefore this is less than or equal, numerator is less than or equal to 1. And denominator as it is I am writing n. Since n belongs to natural number set, no need to keep modulus. So therefore togetherly this one I can write. So modulus of an is less than or equals to 1 by n. Why I am doing all these things you will understand. Okay. Then remove modulus of this. Then what will you get? Minus 1 by n is less than an is less than 1 by n. Look at. Now what is the lower bound? Minus 1 by n is the lower bound. What is upper bound? 1 by n is upper bound. Now this lower bound minus 1 by n is like sequence Bn now here. Look at. The sequence Bn is like my minus 1 by n. And what is upper bound? Cn. Cn is nothing but this one is my Cn. 1 by n. So both are converging to same limit. Now look at. So therefore as n tends to infinity minus 1 by n is 0. As n tends to infinity 1 by n is 0. Therefore indirectly upper and lower bounds, upper and lower sequences are converging to 0. Therefore middle also converging to 0. That's it. So therefore, okay, that is indirectly what I can write. So that is limit n tends to infinity. So Bn I am writing here. Okay, Bn which is limit n tends to infinity. What is Bn here? minus 1 by n, which is 0. Okay, and similarly limit n tends to infinity Cn. Now Cn is nothing but upper bound, so limit n tends to infinity, that Cn is 1 by n, which is 0. So both are converging to same limit, so therefore by sandwich theorem, okay, by sandwich theorem, limit n tends to infinity, the middle one an, which is nothing but limit n tends to infinity. What is middle one? Minus 1 whole power n by n, which is also converges to 0. So therefore the given sequence an is converges to 0 as n tends to infinity. That's it. So you can attack by using sandwich theorem also. So in this sandwich theorem, what you understood, you need to find proper upper and lower bounds, such that what kind of proper upper and lower bounds, such that both are converging to same limit. Such kind of limits only you need to find out. For example, lower bound is converging to some 1 and upper bound is converges to some 0. Then both are not converging to same limit, therefore I cannot apply theorem. Theorem can be applied if and only if both upper and lower limit are converging to same limit only. Okay. Similarly, second in this, so it is not cos n pi, it is make a change, n pi it is, not n, it is n pi. Okay, cos n pi. Yeah, look at now. So now an, nth term of the sequence is cos n pi by n square, or cos n pi is nothing but minus 1 whole to the power of n, right, divided by n square. Because what is cos? So if n is equal to 1, if n is 1, cos n pi become cos pi, right, which is minus 1. If n is 2, it is cos 2 pi. Now what is cos 2 pi? Plus 1. If n is 3, what is cos 3 pi? Cos 3 pi will be minus 1. If n is 4, cos n pi, that means cos 4 pi is 1. Look at it, is minus 1 plus 1 minus 1 plus 1. Like that same thing happens here. Substitute n is 1, you are getting minus 1. Look at n is 1 minus 1. N is 2, minus 1 whole square is plus 1. Look at here also plus 1, like that. So my cos n pi is nothing but minus 1 whole to the power of n. Both are same. Yeah. Now let us find out at what number the sequence is converges. So same thing you can apply by subsequence concept or by sandwich theorem. So then here I can apply. So just find what is modulus of an. This is modulus of cos n pi divided by n square, which is less than or equal to 1 by n square, obviously. So therefore modulus of an is less than or equals to 1 by n square. Okay, so therefore I can write minus 1 by n square less than or equals to an less than or equals to 1 by n square. Okay, now look at both upper and lower bounds are converging to same limit 0. Therefore the middle one also converges to same limit 0. Therefore the middle one converges to same limit 0. That means here I can write, so that means, so therefore limit n tends to infinity Pn, that is limit n tends to infinity. What is Bn? Lower bound, that is minus 1 upon n square, which is 0. Therefore the lower bound, that means the lower sequence, is converges to 0. Okay, so and therefore limit n tends to infinity Cn, that means upper bound. So limit n tends to infinity, upper bound is 1 upon n square, that is also go to 0. Both are going to 0. Therefore by sandwich theorem, I can say that, so therefore limit the sequence an, which is converges to the same limit 0 as n tends to infinity. That's it. Okay, so next one, same by using sandwich theorem. So this problem already I have done by direct limit, so you can do this problem like this also. So directly apply limit n tends to infinity to nth term, limit n tends to infinity an. So limit n tends to infinity an is 1 by 2 raised n What is 1 by 2 raised n is 1 by 2 to the power of infinity is nothing but, what is this? 1 by infinity, which is 0. Therefore, the sequence converges to 0. This I have done already. Not only this, by using sandwich theorem also you can do it. Okay, by using sandwich theorem also you can do it. So directly this will be, here I am writing, so directly will be 0. Or by using sandwich theorem, that is second method, sandwich theorem. You can do number of ways. The only thing is you have to involve in the subject. Okay, yeah. So by sandwich theorem I want proper upper and lower bounds. So here an is 1 upon 2 power n. So every time don't apply modulus both sides. Okay, previous one some negatives are there, that's why I have applied modulus on both sides, but here there is no negativeness. Then we need to approach in a different style. So I need to find a proper upper and lower bounds for this an such that both are converging to same limit. Okay, now look at here. So since n 2 power n is always more than n, right? For n belongs to natural number set, is always true. So therefore 1 by 2 power n is always less than 1 by n. So therefore I can say this is less than 1 by n. Understood? So therefore this is upper bound. Now I need to find lower bound, the proper lower bound. So since, so let's say this is 1, this is upper bound, okay? And since all the terms are positive, all the terms are positive, okay? All the terms are positive, therefore I can say that an, which is 1 upon 2 raised n, which is always more than 0, right? Always more than 0. So it is less than or equal. So it is more than or equals to, as n becomes, if n is infinity, 2 power infinity is infinity, and this is also some sort of. So therefore, let us write less than or equals to, and this is more than or equal to 0. Okay. Let's say this is number 2, second inequality, since all terms are positive. Now from 1 and 2, what I can say, from 1 and 2, 0 less than or equals to an, which is 1 upon 2 raised n. This one is less than or equal to 1 upon n. Look at, both are converging to same limit now. Look at, lower bound is converging to 0, and upper bound is also converging to 0 as n tends to infinity. Therefore this one also converges to 0. That's it. See, remember one thing, why I have chosen only 0. Here 0 will be the lower bound. Any number less than 0 also a lower bound, because lower bound is not unique, right? According to definition of lower bound. So therefore I can say 1 by 2 power n is more than minus 1 I can write. Because this is also, it can be also a lower bound. It is true always. Minus 2 also true. Minus 3 also true. Any number which is less than 0 also a lower bound. But if I take here minus 1 here, if I take minus 1 here, minus 1 less than or equal to an less than 1 by n. Look at, lower bound is converges to minus 1, but upper bound converges to 0. Both are converging to different limits. Therefore theorem cannot be applied. That's why you need to choose proper upper and lower bounds such that both are converging to the same limit. Such kind of upper and lower bounds are required to apply sandwich theorem. Hope it is very clear. Okay. So therefore, here lower bound I can take, for the time being it will be 0. Okay. So therefore lower bound is converging to 0 and upper bound is converging to 0. Therefore the middle term is converging to 0. Therefore final conclusion by sandwich theorem, the sequence an, okay, which is converges to 0 as n tends to infinity. That's it. So this is by using sandwich theorem. Next one, last definition, oscillatory sequences. A sequence an is said to be oscillate finitely if an is bounded and not convergent. The sequence an should be bounded and not convergent. Example, look at this sequence. So now in this, what are the terms of the sequence? If n is 1, it will be minus 1. N is 2, plus 1, minus 1, plus 1, like this. So these are the terms of the sequence, right? Right? Therefore, clearly I can say that minus 1 whole to the power of n, minus 1 whole to the power of n. See, an is bounded. So I think from here onwards it is not visible. So here, this will be not convergent. I'm writing here and not convergent. Because of video here, I think you are unable to see this, and not convergent you write. Okay. If an is bounded and not convergent, that is called oscillatory finite. So therefore minus 1 whole to the power of n is always bounded below by minus 1, bounded above by 1. Okay. So therefore here the sequence is bounded, but this is not convergence, it is bounded. Bounded, but not converges. But not converges. It is already proved in by subsequence concept. Minus 1 whole to the power of n is not converges. So it is bounded but not converges. Therefore this is an example of a oscillate sequence, oscillate finitely sequence. Okay. Next one. A sequence A is said to be oscillate infinitely if the sequence is neither bounded nor diverges to infinity or minus infinity. That means it cannot be infinity, diverges to infinity, and it cannot be diverges to minus infinity. It can be diverges to both. Example, look at this. Minus 1 whole to the power of n into n. What are the terms now? If n is 1, you will get minus 1, plus 2, minus 3, plus 4, minus 5, plus 6, minus 7. So like this. So these are the terms of the sequence. Okay. Now, so is it bounded? So you cannot find small m less than or equal to a n less than or equal to k m. Such m and small m and capital M does not exist. M and capital M does not exist. Therefore, it is not bounded. Does not exist. So therefore, sequence A n is not bounded. Is not bounded. What about convergence status? Since the terms are negatives and positives, therefore let us find two subsequences and finding what is A to n. Okay, sequence A to n. Now what is A to n now? Find out A to n. So A to n, which is wherever n, there you write 2n minus 1 whole to the power of 2n into 2n. So what is this? Minus 1 whole to the power of 2n is plus, so only just 2n only, right? Only 2n. So that means, so limit n tends to infinity, okay, A to n. How much it is? So limit n tends to infinity to n, which is nothing but infinity, plus infinity. Similarly, second subsequence A to n minus 1. Nth term of second subsequence is to A to n minus 1, which is wherever n, there you write 2n minus 1. Minus 1 whole to the power of 2n minus 1 and 2n minus 1. That's it, which is minus 1 whole to the power of 2n minus 1 is always negative. So minus of 2n minus 1. That implies, so limit n tends to infinity, n tends to infinity. Now what is A to n minus 1? Which is, what is that? Limit n tends to infinity minus of 2n minus 1. This is nothing but minus infinity. Plus infinity and minus infinity. That's what, look at. It is converging to both. It is not singly, it is diverging both. It is not singly diverging to infinity or minus infinity. That's what. So it is neither bounded and nor diverges to infinity or minus infinity. Such a sequence is said to be oscillate infinitely sequence. Okay. And with this sequence is over. In the next class I will start with series, and with this I will stop.